Okay, so we left off last class talking about how we would classify something as insoluble or soluble, or in other words, as a solid product. So these ones would be solids, or the ones that are soluble, aqueous solutions. Okay. So we were using a chart to do that. This one, we're looking at these things being soluble. These alkali metals are always soluble. Ammonium is always soluble. Nitrates are always soluble. Okay. Acetates, bicarbonates, chlorates, perchlorates, those are always soluble. So these are the soluble compounds. These are the insoluble compounds. These are insoluble unless you put them with an alkali metal, one of these. Okay. Then they will become soluble. All right. So let's try an example here. Predict what happens when potassium phosphate solution is mixed with a calcium nitrate solution. We're going to write a net ionic equation for this reaction. So net ionic equations, if you remember, we write those by writing out the equation in its ionic form, and then we cancel everything that is the same on both sides of the reaction. Okay, so that's the ionic equation. This is the net ionic equation. This one shows what actually happened. Barium and sulfate found each other and became barium sulfate. The sodiums and the chlorines, they just remained aqueous. So they just remained dissolved in the solution. So they're not going to actually participate in the reaction. So here we want to predict what happens when potassium phosphate, K3PO4, plus calcium nitrate react. Okay? So this is going to be a double replacement reaction. That means the cation ions are going to switch partners. So go ahead and predict the products of that reaction. Now when you predict the products of this reaction, you're going to have to consider the charges, because you have to write the correct formulas for the products. So take a moment and try to figure out what is this going to become. Okay, so what do you guys think the products of this will be? What is it going to make? Okay, Ca3PO4, and there's two of them. Excellent. Okay, so calcium phosphate and KNO3, potassium nitrate. Those both have -1 and +1 charges, so it's just 1 and 1. Okay, good. So those are the products of this reaction. Because it's a double replacement, the potassium goes with the nitrate, the calcium goes with the phosphate. Okay. Now the question is, Are these soluble or insoluble? Yes.
Where did we get the 2 for the PO4?
Okay, so calcium has a 2 positive charge, right? So we have Ca2 plus, phosphate, PO4. Here we can even see PO4 has a 3 negative charge, okay, 3 minus. So that if they come together, that means I need 3 calciums and 2 phosphates.
Okay, so they switched.
Yeah, so these, okay? So that's how I get those, okay? That's what I get. Now I want to write, okay, so I want to identify, so these are aqueous. That's how we can use them, okay? And the question is, are these soluble or insoluble? So look at this one first, potassium and nitrate. Look at potassium. Where's it found on the periodic table? First column, that's an alkali metal. What do we know about alkali metals? They are soluble. Nitrates are also always soluble. Okay? So, aqueous. Now, what about calcium phosphate? So let's go back here. Let's look for phosphates. Here's the phosphates. Okay? Phosphates are insoluble unless they are with an alkali metal. Is calcium an alkali metal? It's not. Okay? So that means this is a insoluble solid product. Okay? So this is my equation. Now, take a minute, write the ionic equation, the entire ionic equation for this. Okay? Okay, so if I'm going to write the ionic equation, I'm going to break it up. K plus PO4 3 minus plus Ca2 plus NO3 minus produces Ca3 PO4, 2 of them, because it's a solid, plus K plus NO3 minus. Now, this was the only solid thing, that's why I kept it together. So, if it's a solid, you're going to keep it together, okay, even in the ionic equation. Everything else is aqueous. This is aqueous. This is aqueous. This is aqueous. This is aqueous. Oops, this is aqueous. And this is aqueous. So everything else is dissolved, okay? But now I have to check to see what's the same, okay? I have K pluses and NO3s on both sides of the equation. So I can eliminate those. What are those called? Spectator ions. Those are spectator ions. They are doing absolutely nothing. They're the same over here as they are over there. So because they're doing nothing, I can eliminate them from this. They're not participating in the reaction. So what is the net ionic equation? The only thing that's actually happening. Calcium 2 plus PO4 3 minus is reacting to produce calcium phosphate, which is a solid, and these are aqueous. Okay? So this right here is my net ionic equation.
How come you don't put the two NO3 on the left side? Because you know how you have two of them on the left side?
Oh, well, yeah, that's a good point. So if you can balance it. If you balanced it, you would. I didn't balance it.
Oh.
But balancing it is always appropriate. But it's not necessarily necessary to determine this. So here, if I balance this last thing, I would say I need 2 phosphates, 3 calciums, right? And now that's a balanced chemical equation. So, but yeah, it's just because I didn't balance it up top. But to determine the ions or the product, I don't need to balance it, but it is appropriate to balance this, especially in the end. You're right. That would be appropriate. Okay. So now we're going to talk about acids. So we've talked about different types of reactions. That's what we're trying to do. We're trying to identify different types of reaction: combustion, decomposition, single replacement, double replacement. Double replacement are precipitation reactions. These precipitation reactions, we can predict whether it's a soluble or insoluble thing using that chart. And now we're going to talk about acid-base reactions, okay? And then oxidation reduction. So what are some properties of acids? Acids have a sour taste to them, like vinegar or citric acid. Lots of candies, sour candies have citric acid, right? So it's that sour taste. They often react with metals to produce hydrogen gas through a single replacement reaction, right? The magnesium replaces the hydrogen. The hydrogen comes out and becomes H2. Okay? So acids will often give you hydrogen gas. That's a good way to produce it. And reacts with carbonates and bicarbonates to produce carbon dioxide. Okay? So here we see acid plus this calcium carbonate produces calcium chloride, and this carbonate, the CO3, would actually produce H2CO3, carbonic acid, which would then decompose into carbon dioxide and water, and you produce carbon dioxide gas. Okay, and a very common reaction to show that as well is if you take something like an acid, HCl, and a bicarbonate. So see the bicarbonates plus HCO3. So let's say sodium bicarbonate. Who knows what sodium bicarbonate is? That's baking soda. Okay? So sodium bicarbonate, baking soda. You react it with an acid, or not even hydrochloric acid. You could react it with another acid, common acid, vinegar. Okay, vinegar is an acid. And that's acetic acid, CH3COOH. That would produce sodium acetate plus H2CO3. Whoops, H2CO, yeah. And then that would decompose into, the H2CO3 would decompose into H2O plus carbon dioxide gas. This is a gas. Okay? So if any of you have ever done the famous volcano, right, that everybody does for science fairs or whatever, Okay, they use vinegar and baking soda in there, you know, because all that carbon dioxide gas that's produced, it just kind of creates that situation where it's foaming out, right? Because of all the gas that's coming out with it. Acids can conduct electricity because they are electrolytes, right? So HCl is a strong acid, and it dissociates into H plus Cl minus. So they are electrolytes in if it's aqueous. Okay. So they will conduct electricity. Acetic acid is also an electrolyte, except it is a weak electrolyte because it dissociates into these ions, but creates this situation where that hydrogen is coming on and off, on and off. And so this one, strong acids have 100% dissociation of the hydrogen. Weak acids or weak electrolytes have only a partial ionization of that hydrogen coming on and off. Okay? So that's why this one would conduct electricity better than this one at the same concentration. At the same concentrations, this would have more ions present and therefore would conduct electricity better than this one. Okay? Which is a weak acid, weak base. Okay, bases. They are bitter, so instead of being sour, bases are bitter. They have bitter taste. If you've ever tasted baking soda is a base, and it has a very bitter taste. Okay, so if you put too much baking soda in your cookies or something, it tastes very bitter. So that's where that's coming from. Their bases are often very slippery. A lot of soaps have bases. Aqueous-based solutions conduct electricity because they're also electrolytes, just like we saw with acids. They can dissociate. Sodium hydroxide is a strong base. It dissociates into Na plus OH minus. Okay, NH3 is a weak base. Okay, it's a weak base because in the presence of water, it will become NH4 plus OH minus, but in equilibrium. Okay, so these are electrolytes. Okay, and we're going to define further what an acid and a base is so that we can understand this context of how we define these as bases. Okay, and hopefully you can see that partly that they're producing hydroxide OH minus in solution, and that's the basic ion. Okay. So we have this. The first definition that we have here for an acid and a base is the Arrhenius definition. And basically, Arrhenius defined it as something that produces H plus in solution in water. Okay. So if it's an acid, it will produce this H plus. If it's a base, it produces OH minus in solution. Okay, and you can see that happening here with the hydrochloric acid and with the ammonia as well. Okay, this one it's less clear that that's what it's going to do because you have to have water for it to react with in order for it to produce the OH minus, which is often the case with lots of weak bases. Weak bases, you often have to have water in order to produce that hydroxide. So we like to take this a little further, okay, and define it a little better. So instead of so now we have a Bronsted acid and a Bronsted base. This is the definition that I really want you guys to really learn because this really describes it very well as to what's happening, okay? So here we have an acid defined as a proton donor and a base as a proton acceptor. Well, what do I mean by a proton? Well, if you consider hydrogen, here's the nucleus of hydrogen. It has one single proton, right? Atomic number 1. That means it has one single proton in its nucleus. Surrounding it is one energy level with one single electron. That's hydrogen. Well, if it becomes H plus, how would I redraw this as H plus? What's that? I remove the electron and the energy level. What am I left with? I'm left with a single proton. So that's what they mean by a proton donor or a proton acceptor. Okay? So if you are a proton donor, you're producing H plus, or you're donating a hydrogen, a positively charged hydrogen, which is a single proton. That's what an acid is. It's a proton going around and doing chemistry. That's an acid. Okay? So if you donate that proton, you are an acid. If you accept that proton, then you are a base. Okay? So if we look at ammonia here, it reacts with water. Okay? So the water donates the hydrogen to ammonia. Do you see that? And you're left with OH minus and NH4 plus. So the base is the thing that accepts the hydrogen. The NH3 accepted the hydrogen, became NH4 plus ammonium, and we're left with OH minus. Okay? So that's how we define this as a base. All right? Now when we look at this, and we see that we have ammonia over here and ammonium over here, we say that these are conjugates. They're conjugates. This is the base, and this is its conjugate acid. If you're a base, you have a conjugate acid. If you're an acid, you have a conjugate base. Okay? So we're saying this water is the acid, so its conjugate base in this situation would be hydroxide. Okay? So this is where we label the acid and the base on the reactant side, and on the product side we label them as the conjugates of those. Okay? Because they, especially in an equilibrium situation like this, where it goes back and forth, it can go back and forth. Right? So here's some monoprotic acids, which means there's a single hydrogen to donate. Okay? HCl is a strong electrolyte, strong acid, because it dissociates 100%. Notice the single arrow. That's indicating it goes one way. It doesn't go backwards. Okay? Nitric acid, also strong donation of that hydrogen. The hydrogen stays off. Okay? But then when you see acetic acid, you'll notice that the acidic hydrogen comes on and off. It goes on and off, on and off. So this is a weak acid or a weak electrolyte. That's how you identify weak and strong acids as to whether they are weak or strong electrolytes. If it's a strong electrolyte, that means dissociation is 100%, therefore strong electrolyte, strong acid. Weak electrolytes, weak acids. Okay? Now you'll notice that this acetic acid has more than just one hydrogen, but the other three hydrogens, these ones right here, they are not acidic hydrogens. So if I drew the structure of this, it would be more like something like this. Okay? So, where's the acidic hydrogen? It's right here. These ones are not acidic. They will not come off. They're covalently bonded to this carbon. This hydrogen is bonded to this oxygen, but it's with a kind of a weak bond because of all the electron character, especially from this double bond that's pulling electrons this way. So I'm pulling electrons from the oxygen from the hydrogen and then up this way. And so it weakens this attraction, and that hydrogen falls off. This is called a carboxylic acid group. You'll learn about that in organic chemistry. Okay? So this carboxylic acid, this hydrogen will fall off, and now I'm left with acetate. Okay? This is the acetate ion, polyatomic ion. Okay, so that hydrogen will come on and off. So it's a weak acid. So it's a monoprotic acid because it only has one acid or hydrogen that can come off. But you can see here things like H2SO4 and HSO4. These are diprotic. Well, H2SO4 is a diprotic acid. The first step, the first hydrogen that comes off, strong step. That hydrogen comes off 100%. But you see I have another one. That next one only comes off part of the time. Okay? And so I get an equilibrium. Triprotic acids, like phosphoric acid. Weak steps all around, all three of them. Okay? So I get an equilibrium with this one. This is the strongest step, but it's still a weak acid step because there is an equilibrium here. Okay? But then this one's weaker and will come off to an even lesser extent than this one. And then this one is the weakest step. So most of the hydrogen that is being ionized is essentially from this first step. So if you consider the total concentration available, if this one came off and is providing a hydrogen ion concentration of 0.0013 or something like that, and the next one comes off and is producing, okay, you can see how insignificant that is compared to this, right? So it's hardly significant. These ones hardly become significant at all. And this third one, you know, it's coming off to a really tiny amount. Okay, and so it would end up being that this isn't really considered very much into the concentration of this one. So this one ends up being essentially the concentration of that high acid solution. Okay.
So it's one arrow is strong electrolyte, 2 arrows electrolyte.
That's right. That's exactly right. Okay, so here's some common strong and weak acids. Okay, and everybody always asks me, Mr. Crandall, how do I know if it's a weak acid or a strong acid? And there are reasons that it's a strong acid or a weak acid, and but the best way is to just kind of try to recognize what are the weak acids and what are the strong acids. So things like hydrochloric acid, hydrobromic acid, hydroiodic acid. Okay, those halogens, those are strong acids. Okay, except for HF, hydrofluoric acid, right? This is not a strong acid. This is a weak acid. You're like, I've heard hydrofluoric acid is pretty nasty acid. Yeah, it is. It's still an acid, and it will dissolve your hand, sure. Okay, but you want to consider it as a weak acid because it has an equilibrium step. It's not a very, it's not of the weak acids. It's the strongest weak acid. Okay, HF is, but it still has a equilibrium. So we have to consider it a weak acid, okay? But these are strong acids. HCl, HBr, HI. We consider those to be 100% dissociation, okay? And so they're strong acids. Nitric acid, strong acid. Sulfuric acid, remember, sulfuric acid, diprotic acid, it's only the first hydrogen. That's the strong acid step. The second hydrogen would come off in a weak acid step, okay? Perchloric acid. So one thing that you can notice here is look at the hydrogen to oxygen ratio. Lots of oxygens, 1 hydrogen. Lots of oxygens, 2 hydrogens. Lots of oxygens, 1 hydrogen. So because there's so many oxygens, that weakens that hydrogen attraction to the acid, and it allows it to come off. And that's why it's a strong acid. So when we get into these weak acids, look at this. 2 oxygens, 1 hydrogen. So HNO3, strong acid. HNO2, weak acid. Okay? H3PO4, lots of hydrogens, lots of oxygens. But because my oxygens don't outnumber my hydrogens by a lot, that ratio of hydrogen to oxygen, this is a weak acid. Okay? Acetic acid, weak acid. Okay? Same thing, just a few oxygens to the hydrogen ratio. And so it comes off in a weak acid step. Hydrofluoric acid is a weak acid. We discussed that. Okay? And that actually has to do with the size of the atom. So as you go down here, it's getting bigger and bigger and bigger. This is actually, of these strong acids, this is the strongest. The hydrogen has the hardest time holding on to iodine. It has the easiest time holding on to fluorine. Okay, so that's why this is the weak acid, but these ones are strong. It has to do with the size of the atom in that case. Okay. So let's classify these as bases. Classify each of the following in aqueous solution as a Bronsted acid or a base. So HBr, that's going to be an acid. It's going to donate hydrogen, right? Okay, NO2 minus. Good. So it's going to react with water. It's going to pick up a hydrogen and become HNO2 plus OH minus. So it is a base. It picked up that hydrogen. And you're left with OH minus. So it is a base because it accepted the proton. Okay, HCO3 minus.
Acid.
Okay, acid and base. Okay, so you could consider it this way. HCO3 minus can either go to CO3 2 minus, or it could go to H2CO3. Right? So, in that case, HCO3 minus going this way is acting as a what? Going that way, it's acting as a base because it's accepting a hydrogen, right? Going this way, it's acting as a what? Acid. Okay? So, whenever you have these diprotic acids, a lot of times you have that middle guy that can go either way. It depends on what it's reacting with. If you're reacting this with something that's a stronger acid than it acts as a base. If you're reacting this with, and it's the stronger acid, then it acts as the acid. Okay? And it will go that way. So, when it's in the middle there, it can go either way. Okay, so neutralization reactions for acid and bases simply is when you react an acid with a base, and if we write the ionic equation for that, you see H plus, CO minus, sodium plus, OH minus. Okay, this is a strong acid, this is a strong base. What do I produce from that? Well, it's a double replacement reaction. So I get NaCl, sodium chloride, and H and OH, water. Okay, so I took the H plus, which is the acid, the proton, and the OH minus, which is the base ion, and I reacted them together to form water. And water is neutral, right? That's how we would consider it. We'd say water is neutral. So what is the net ionic equation for an acid-base reaction? H plus plus OH minus produces H2O. Because look at this, sodium chloride is aqueous. So it's not really, it's spectator ions. These are spectator ions, the sodium and the chlorines. Those are spectator ions. So they are not participating in the reaction. They're just left over. It's the H plus and the OH minus that have neutralized each other into water. Okay? So in that concept, that an H plus and OH minus neutralize one another is an important concept because we will use that in order to determine concentrations of acids and bases that are unknown to us. Because if we know the concentration of an OH minus, but we don't know the concentration of the H plus, we can react them to determine one or the other. Okay, that's called a titration. We'll look at that then later in this chapter. Okay, so how about a weak acid plus a base? So I'm going to react a weak acid with a strong base. So here's my sodium hydroxide, it's strong. Here's my weak acid, hydrogen cyanide. Hydrocyanic acid, excuse me. Hydrocyanic acid, sodium hydroxide, double replacement, right? So the sodium cyanide. And then what do I still have? I still have it's weird. This was not right. This should be H plus Cn minus. Okay? Okay? So I get the sodium and the cyanide coming together, and then I get the H plus and the OH minus. Should just be H plus. Okay? Okay? And I'm going to be left with sodium cyanide and water. These two things and water, and then water comes, and that is my reaction. Once again, acid with the base to form water. Okay? Okay, so let's write the molecular ionic and net ionic equations for the following. Okay? So we have HBr, hydrobromic acid. Now remember, naming acids, I use hydro when it's not the oxy acid. If it was an oxy acid, it would just be bromic acid instead of hydrobromic acid, which would be for bromate, BrO3 minus. Okay? So HBrO3 would be bromic acid. Hydrobromic acid is HBr. Okay? So I have HBr plus barium hydroxide, barium, OH2. Okay? Barium has a 2 positive charge. Hydroxide has a -1 charge. So I'm going to have 2 hydroxides for every 1 barium in this form. Okay, so that's going to react, goodness, to form what? Barium bromide plus water, right? Okay, sulfuric acid, H2SO4, which is different than hydrosulfuric acid, which would be what? If it was hydrosulfuric acid, what would the formula be? It would be what?
Without the oxygen.
Okay, H2S. That would be hydrosulfuric acid. Okay, so not the oxy, just the element. Okay, sulfur has a -2 charge, so that means it has 2 hydrogens attached to it. So sulfuric acid plus potassium hydroxide. Okay, so what am I going to get here? Remember, it's just the first hydrogen that we're really going to consider well, no, we'll consider both of them because it's a strong base. It's going to pull both of those hydrogens off, that strong base.
Is it KSO4?
Okay, potassium sulfate and H2O. Okay, because you're going to get, for every, a hydroxide is going to pull this off, and then we could balance it, of course, but that's what you're going, those are going to be the products of this reaction. Okay. Okay, so let's go ahead and write the ionic equation for A. We have H plus Br minus plus Ba2 plus OH minus. produces Ba2 plus Br minus plus H2O, which is a liquid, so it stays together. This is a liquid, this is a liquid, these are aqueous. Okay, so this is going to be my ionic equation. What are my spectator ions? Barium and bromine, right? Those are my spectator ions. What's my ionic equation? Net ionic equation, excuse me. That's the acid-base reaction, okay? That's the net ionic equation for an acid-base reaction. Okay, the same thing is going to be true for this one. I can see potassium and sulfate are my spectator ions, right? So those are my spectators, potassium and sulfate, and I'm left with H plus OH minus to produce H2O liquid. Okay, so that's going to be my ionic equation, net ionic equation. Okay. So they're strong bases, yay. Okay, barium hydroxide, they're going to produce water. And here it is, and it's balanced now. Okay, so these are our spectator ions. They're going to cancel. You're going to be left with H plus OH minus produces H2O. Okay. All right. Potassium hydroxide, K2SO4. The potassium and sulfate are the spectator ions. Okay, and they're just showing it in both steps here. So it will go down to the SO4 plus the plus water at the end. Okay, so you're going to get rid of both of those hydrogens off there, and you'll be left with that final water, and the H plus and the OH minus produces the water. Okay. Okay. So here, simply, if you react an acid, a strong acid with a base, okay, you're going to produce a salt plus water. In this case, we're going to produce one with carbon dioxide because this is a carbonate, okay, and that carbonate is going to decompose into water and carbon dioxide. Okay, so we're going to produce this. This would first go from H2HCl plus Na2CO3 to become H2CO3 carbonic acid plus sodium chloride. Okay, and then the carbonic acid you can see decomposes into water and carbon dioxide, and that's how we get our water and carbon dioxide. Okay. So that's a very common thing that happens with baking soda or other carbonates, okay, that you react them with the acid. Okay, now let's talk about oxidation reduction reactions. So hopefully you'd be able to identify an acid-base reaction, okay, a precipitation reaction, an acid-base reaction. Now let's talk about oxidation reduction. So acid-base, we're transferring protons, hydrogens, okay? But in oxidation reduction, we are transferring electrons. The electrons are going from one thing to another thing, okay? So just like in acid-base, you lose a proton, something is the acid, something is the base, something's You're losing hydrogen, something's accepting that hydrogen. Okay? In oxidation reduction, something is losing electrons and something is gaining electrons. Okay? There's always, you always have to be able to account for all of your electrons. They don't just go away or disappear. They go somewhere. Okay? So we have to be able to follow them. So here's an example, magnesium. Magnesium, when it becomes ionized, it loses electrons. Okay? How many electrons does magnesium lose to become magnesium 2+? 2 electrons, right? So it's going to lose 2 electrons. Well, does magnesium just lose electrons because it decides it wants to? No. So why does it lose electrons? It loses electrons because something it comes in contact with has a greater affinity for electrons than it does. And because that thing has a greater affinity for the electrons, it happily gives it to it. Okay? And so here we see oxygen. Oxygen has a stronger affinity for electrons, and so oxygen gains those electrons that magnesium donates. Okay? So there's a complete gain and loss of electrons in this reaction. So magnesium reacting with oxygen, magnesium plus oxygen, and we have 4 electrons. The 4 electrons are transferred. Okay? We eliminate those. And you'll be left with this equation. Magnesium plus oxygen produces magnesium oxide. Okay, balanced, we have 2 and 2. Okay, so this is the idea behind oxidation and reduction. Oxidation is a loss of electrons. Reduction is a gain of electrons. Reduction is when you gain electrons. Oxidation is when you lose electrons. Okay? That's going to be confusing sometimes, so remember that oxidation is loss and reduction is gain. Oil rig. Okay? Oil rig. That's how you can remember it. Okay? Oxidation is loss, reduction is gain. Okay, so here we can see we have some zinc in a copper sulfate solution. Okay? The solid piece of zinc, see the zinc atoms, they're all together, they're solid. Okay? Well, zinc has less of an affinity for electrons than copper. So copper, when it in its copper 2+ state, wants its electrons back in the presence of zinc. So if you stick zinc in a copper solution, a copper 2+ solution, then those electrons will be pulled off of zinc and put back onto copper. And you can see what happens. Copper starts to plate around the zinc, and the zinc ions start to come off. Okay? So the copper starts to build up around here. That's what it's doing. And the zinc is beginning to dissolve. Here's another example. Here's some silver ions in solution. Those silver ions, they want electrons back. They're missing 1 electron. They want it back. Or they have a greater tendency to want it than copper does. So that silver can steal the electron away from copper. The silver ion can steal it away from copper. So copper will give it away, silver will accept it. Okay? And so then we get this situation where the copper wire that's put in here starts to get silver building up around it. And the copper begins to dissolve. And that's why it turns blue, because copper ions are blue. So it was a solid piece of copper, but now it's becoming ionic because those are dissolving into it. So whenever you put something in the presence of something else that has a greater affinity for electrons, they will steal those electrons. They will steal them away. And in fact, if you separate the two and put a wire between them so that electrons can pass from one thing to the other, then that's a process that we call conducting electricity. You can conduct electricity spontaneously by simply separating these two metals away from each other and putting a wire between them. Okay? So, and we'll look at that more, but here's another example. Okay? So zinc goes from zinc to zinc 2 plus. That means it lost 2 electrons. So zinc is oxidized. Okay? So here we can see that. Here's zinc. It's has no charge, right? It's at 0 charge. Over here, the zinc has a 2 positive charge with the sulfate. Okay? So that's how we know it went from zinc to zinc 2 plus. The copper is at copper 2 plus, and it goes to copper solid at a 0 charge. Okay? So copper 2 plus to copper. So that is reduced. Zinc is oxidized because it what? Loses electrons. Oxidation is loss. Copper is reduced because because reduction is gain. It gained electrons. Okay? So that's how I would identify it from this reaction right here. What was reduced, what was oxidized. So I would come up here and I would say zinc is oxidized, copper is reduced. Okay? Now, if you are reduced, then what caused you to become reduced? The other thing. Okay? So copper was reduced. What caused copper to become reduced? Zinc. So that means zinc is the reducing agent. Well, if I is oxidized, zinc was oxidized, what caused zinc to lose electrons? What forced it to lose those electrons? Copper. So it's the oxidizing agent. Copper 2 plus was the oxidizing agent. Okay? And this is one thing you need to be able to do. A lot of times the question is, what is the oxidizing agent? Or what is the reducing agent? That means you have to identify what was oxidized, what was reduced, and then answer the question, what is the oxidizing agent? What is the reducing agent? Okay? So if I'm going to do that, if I identify successfully what is oxidized, then it's easy to know that if I was oxidized, I am the reducing agent. If I was reduced, I am the oxidizing agent. Okay? So I'm the opposite on the other side. So over here, I'm oxidized. Over here, I'm the reducing agent. Over here, I'm reduced. Over here, I'm the oxidizing agent. Okay? So you first identify the products, and then you can identify what the reactants are. They're the reducing or oxidizing agent. Okay? So they're simply the opposite of that. Okay, now, how are we going to be able to successfully identify whether something was oxidized or reduced? Well, we have to be able to identify their oxidation number. Oxidation numbers can be kind of tricky. So you're going to have to pay attention how we do this. Okay? So first off, if something is in its elemental state, okay, sodium, beryllium, potassium, lead, hydrogen, oxygen, phosphorus. Do you see how these are all in their elemental state? Okay? These are diatomic, but that's okay. That makes them to 0. Okay? That's how they exist in nature. How I find these elements in nature, that means they're at a 0 oxidation state. Okay? They are at 0. Okay, so far, not too bad, right? That's not hard. Now, if you are a monoatomic ion, if you're an ion, okay, your oxidation number is equal to the charge of that ion. So if you're an ion, then we know your oxidation number. We know the oxidation numbers of all the first elements. It's +1. All the second elements, +2. Okay? So those ones, not too bad. And oxygen. Oxygen is a constant that we can rely on. to be -2 in most cases, okay? Unless it's in peroxide, H2O2, it has a -1 instead of a -2, okay? But that's one of the only exceptions to that. Oh, here it is. It's a -1, okay? So that's one of the only exceptions to that oxygen, okay? Oxygen is almost always -2 unless it's a peroxide, and then it's -1, okay? So if it's an ion, we know its charge. It's a 3+ or a +1 or whatever its charge is, okay? The oxidation number of hydrogen is +1, so that's another thing we can rely on. Hydrogen, +1, except when it is bonded to metals in binary compounds. In binary compounds, it is a -1, okay? But for the most part, hydrogen is always +1. Okay, group 1A metals +1, group 2A metals +2, that's what we said, +1, +2. Fluorine is always -1. There's another constant, okay, -1. So what we're trying to do is tell you the things that you can count on, because there's going to be lots of other elements. All of these other elements you can't count on. You can't count on them to have a constant oxidation number. Their oxidation numbers can be all over the place, okay? So that's why we're telling you this is what you can count on. These are going to be your clues as to when you try to find the oxidation numbers of the things like nitrogen that you can't count on. I can't count on a nitrogen. It can have all kinds of oxidation states, okay? So I can't count on it. Okay. So we did that, okay? -2 mostly for oxygen, okay? +1 for hydrogen. Group 1A is +1, group 2A is +2. So this is how we would identify these oxidation numbers, okay? So let's assign oxidation numbers to these elements, okay? So remember, group 1A metals I can count on. Lithium has what oxidation number? +1. Oxygen has what oxidation number? -2. Okay? Okay, not too bad, right? Okay. Let's go here. What is the oxidation number of oxygen in HNO3? -2. But there are 3 of them, so overall, the oxidation state is, for the oxygens, all 3 of them, would be -6. Okay? What is the oxidation number of hydrogen? +1. Okay? So, it's +1. Now, when I say what is the oxidation number of oxygen, it's -2, not -6. So if the question asks you what is the oxidation number of oxygen, you answer it -2. Because if you put -6, it's wrong. The oxidation number in this compound of oxygen is -2. Okay, is that clear? Because a lot of people put this. That's wrong. This is the oxidation number of oxygen in this compound. The fact that there's 3 of them means that to figure out what the nitrogen is, I have to figure out that I have a -6 charge here. I have a +1 charge here. What's left? 5 positive charges, right? So what is the oxidation number in this compound of nitrogen? +5. Okay? So nitrogen has a +5 oxidation state in this compound. This is not an ionic nitrogen. If it was ionic, it would be what? -3. Nitrogen is not ionic in this compound, right? This is a molecular compound. The oxidation state of nitrogen in that compound is +5. Okay? Why?
Yes.
Well, are you saying why? How did we figure that out? Okay. So here we have a -6 charge. Here we have a +1 charge. So I need 5 more positive charges to balance these -6 charges. So that's why it's +5. Because I have to have +6 charges over here to balance the -6. Okay?
Yeah.
has an oxidation state of +5. Okay? So that's its oxidation state, which is different than an ionic charge of -3, which nitrogen we would predict to be -3. That's different. This is a covalent compound. Okay? Within the covalent compound, it has an oxidation deficiency of +5, electron deficiency of +5, basically. Okay? But that's in the this compound. So it's different. All right? That's why it can become tricky. So that's why we need clues. These are my clues. My clues are the oxygens and the hydrogen, which have a constant charge. Oxygen's oxidation number is -2, unless it's a peroxide. But for the most part, you're not going to see a peroxide. Okay? Very rarely. Okay, now let's look at this one. Kind of got pushed up here, so I'm going to rewrite it. Cr2, O7, 2-. Okay, so oxidation number of oxygen is -2, right? There are 7 oxygens, so that's how many negative charges?
14.
-14 overall that I have to balance. But look at this. A -2 charge left over, right? So that means I'm going to drop this to -12 that I have to balance with the chromiums, because I need 2 negative charges left over. Okay? So I'm going to go to -12, needing -12. What is the oxidation number of chromium? It's +12 for 2 of them. What is the oxidation number for chromium?
6.
+6. Okay? Chromium has a +6 oxidation number. Okay? That's how I identify. So if I was identifying the oxidation numbers of chromium and oxygen here, I'd say chromium 6+, and oxygen is a 2-. Okay? And those are their oxidation numbers. Okay, so you can see all the different oxidation states that all these elements can take. Okay, that's what this chart is showing. Look at nitrogen, +5, +4, +3, +2, +1, and a -3 if it's an ion, right? Carbon has all these oxidation states, +4, -4, it has those two, has all kinds, okay? Chlorine, look at all those states that chlorine has, okay? So you can't just look at the periodic table and say, oh, I know the oxidation number, except for those few that have a constant oxidation number. Those are the trustworthy ones. Those are the ones that you use to figure out the oxidation states of the other things around it. Okay? And we'll practice that, okay? Because you'll need some practice. Okay. Okay, so we'll probably practice it next time. So let's look at this type of oxidation reduction reaction, okay? So combination reaction, A plus B to form C, all right? This can be a oxidation reduction reaction if we have loss of electrons from one thing, gain of electrons from another thing. So this Al and Br, they're both at a state of 0. Here, Al goes to 3+, and Br goes to -1 each. So that's -3 overall. So that's balancing it, okay? So what lost electrons and what gained electrons?
Chromium gained electrons.
Okay, so it is reduced or oxidized? Reduced. That means Al is oxidized. What is the reducing agent?
Al.
What is the oxidizing agent?
Chromium.
Okay, that's how I need to identify this. So from the oxidation numbers, I can determine. So that one's not too bad because it's ionic. So I know the ionic, because it's ionic, I know these oxidation numbers. Okay, that's straightforward. This one's not as straightforward. But look what, okay? So I have to figure out the oxidation states within this compound. All right? So here I have an oxygen, which is -2. -2 is -6 overall, right? For all 3 of these oxygens. Here's a potassium. Potassium's in the very first column. What do we know about potassium in the very first column? That its state is always +1. So I have a +1 charge on the potassium. So I have to balance this -6. I have a +1, so I need +5 more. So that means the chlorine is +5. Okay? So I know the oxidation state of chlorine. Now look what happens when I decompose it. The oxidation state of chlorine goes from +5 to what? -1. KCl. This is an ionic compound. Potassium and chlorine. +1, -1. Oxygen goes from a -2 to what? 0. So what was oxidized? What was reduced? First off, let me say, did potassium change its oxidation state? No. So don't even worry about it. It's not part of this oxidation reduction change. It stayed the same, right? So all we're looking at is the chlorine and the oxygen. Which was oxidized and which was reduced?
Reduced chlorine and oxygen was oxidized.
Okay, oxygen was oxidized because it had -2, had extra electrons. It lost those and went from -2 to 0. Okay, oxidation is loss. So O2 was oxidized. It lost electrons. What gained electrons? Chlorine gained electrons. How many electrons did chlorine gain? 6. It went from +5 to 0 by gaining 5, and then it went to -1 by gaining 1 more, right? So it gained 6 electrons. So it was reduced. What is the reducing agent? Oxygen is the reducing agent. Chlorine is the oxidizing agent.
I'll give you +5 to -1 is a
Sure. Okay, let's consider it like this. Here is a number scale. +1, +2, +3, +4, etc. -1, -2, -3, -4, etc. Okay, so chlorine, actually let me go to +5 over here so we can use this. +5. Okay, chlorine started right here. It had to gain 5 electrons to get right here to 0, right? So that's 5 electrons that it gained. Now it has to gain 1 more to get to -1. So that's 6 electrons overall, right? So that's how it went from +5 to -1. Where did those 6 electrons come from? They came from oxygen, right? That's where they came from. Oxygen gave away those 6. See, I have 3 oxygens, so I get the 3 oxygens over here. These 3 oxygens gave away how many electrons? 6. Where did those electrons? You always have to account for all the electrons. Those 6 electrons came here. Okay? They will always be accounted for, all the electrons.
Professor,
Yes.
the previous one, the previous slide, the oxygen had the 2 minus, maybe one more back than the previous one. The third one, C, 0.7 2 minus.
Mm-hmm.
Why is that 2 minus there? Like, because we have to subtract that from the 14.
So there's an unbalance of electrons in that compound. There's extra electrons that aren't being neutralized, I guess. So I have these 2 extra electrons. So when I figure out how many negative charges I have -14 overall, but I only need to balance 12 of them because I have 2 more right here. Is that answering that question?
I mean, yeah, I get it.
So I have -14.
Yeah.
The other 2, it's because these oxygens have extra electrons on them. So they've picked up extra electrons, and so they're not. But those extra electrons are not being balanced. Okay, this will balance most of them, but just not these last 2. So I have 2 extra electrons on this entire compound that aren't being balanced by a positive charge. Yes?
Information would be written on the equation itself.
This 2 minus?
Well, and where the black is written, it has a 2 minus sitting on top of it.
Yeah.
So it would be written.
You would always have that if it's an ion, it will tell you what the charge is if they want you to balance the ion. Okay, guys, we'll see you next time.